хорошо, it's recording. Say hi, guys.
Yes, yes.
Nice. So again, this course is quite advanced. So I'm going to make a lot of assumptions on the things that you have learned already. These assumptions are going to be stuff like, okay, 1 second. Yeah, nice. So are going to be stuff like neural networks. You've already have some experience, although we will cover them today, but I would really like it if you have some Python experience. You have already worked a little bit with the computer vision applications and stuff like that. You know already what is machine learning, concepts such as overfitting, underfitting, how to solve these things. So these are very trivial and basic concepts that are at the core of this course. Just a small self-introduction. My education, I did my bachelor's in Algeria in computer science. I did my master's with you guys in data science in Innopolis. And currently I'm doing my PhD in Sorbonne University in France. My experience, I've worked with Provectus for a couple of years, and mainly I've worked in Innopolis research labs. I think the machine learning and knowledge representation lab with Professor Khan, and the industrial artificial intelligence center now it's called, right? With Ramil and the other guys, right? My research interests are generally computer vision, domain adaptation. So if you guys know me, you probably know what domain adaptation is because I always speak about it. And now my current topic of research is about combining knowledge graphs and domain adaptation to do, well, to improve computer vision models. If you'd like to contact me, of course, I'm sure many of you have already my Telegram. Usually I respond very fast, so just send me a message on Telegram. Or you can, if you are like a bit shy and don't want to do it, go ahead and send me an email on my email address. And always use this group to discuss ideas or to tell me any kind of problems that you guys are facing, propose any new solutions or stuff like that. You can use the Telegram group and just send me your ideas, okay? Now, this is where I would like to have some conversation with you. So what I assume or what I want is to have a final project, which is 30% of your grade. In this final project, you're going to do one of these three things. So as we said, there are like two kinds of people in this course. So those who are going for the research and those who are going to build industrial applications, right? So the first one is to write a paper. You don't have to publish it. It doesn't have to be super fancy or very difficult, but at least you must understand the, what are they called? The different sections of writing a research paper, how to use LaTeX and stuff like this. So basically, if you can manage to find some idea, explore it, implement it, test it, and write it in a paper, that's going to give you your final project. Another option is to build a product and deploy it. So we will speak later on about what we will cover in the course. But the final few weeks, we will be speaking mainly about deployment and hosting your models, right? Another very important aspect is open source contributions. So for those who are really into hardcore implementations, you can go ahead and find some library online that you would like to contribute to. And that contribution will be counted as your final project. I assume that at least many of you are already working on their proper papers. And if you're not working on your paper for your thesis, then you're probably working on a product for your company. If that is already the case and you are working on something related to computer vision, then that will be counted too, just as long as you have the main contribution in the project. So not like you bring me some project from some of your colleagues and say that it was yours, okay? So something that you have developed yourself. And the final projects will be presented by each person. Sorry, will be presented by each person in the end of the course. 30% will go for like mini projects, which are like homeworks. Basically, after every lecture or after every week of lectures, we're going to have a small Colab link that you guys should just fill in the code, right? It's going to be something very simple. If you have already had the course with the advanced computer vision, advanced machine learning or introduction to machine learning with Professor Khan, then you're already familiar to this kind of projects, right? So in our course, we're just going to have 4, and your final grade will be the 3 best mini projects that you submit. Then we will also have some exams and quizzes. For today's quiz, there's going to be a very small quiz. For today's quiz, it's not going to be graded, but there's going to be 5 quizzes and 2 exams. So basically a midterm and a final exam. Again, they're going to be relatively simple compared to the final project. So the final project should take most of the grade. You're going to see an example of how the quizzes will be made. So quizzes are usually very simple and easy to answer. So this is just something to get your grades up a little bit. The exams might be a little bit tricky. So they're going to be the same style of exams that you are familiar with courses such as machine learning and advanced machine learning with Professor Khan. This is how I see things. Now, if you guys would like to maybe put a final project at like 40% or 50%, there's definitely going to be a negotiation. If you guys would like to not have any exam at all, but focus more on the mini projects and the quizzes, there's not going to be any problem in that. So please feel free now to give me your ideas.
Can I?
I think
Of course, yeah.
first, okay, Nikita, go.
Yeah, thank you. What if we are working on the same project, and how can we tell you the contribution?
Exactly. So basically, if it's a very big project and it's like very well made, technically just show me what you have done. Okay. As long as you can.
Can we show you up front, right? Like right now? So
I wouldn't say right now, because right now we are doing already like the lecture with a lot of people. But right after we finish this lecture, we could have a one-to-one conversation and show me everything you have. I'm sure that there are lots of people who are already very well advanced in computer vision. So that's a very good thing. So something that will really raise the bar for the comparison and competition. Mm-hmm. Any other proposals, guys?
I think, let's see.
Yeah, go ahead.
Sorry,
Ali.
Ali.
Yeah.
Okay, I will, well, Albert. I think I'm making a combine the ideas of me and Jan, and actually like we want to make more like work by hands, like more coding, more like try by our own hands, by understand like in progress and work, for example. This why like I think me and Jan like for the idea to like make more mini projects, for example, making more difficult, for example, more enriched with tasks, but make less exams. It's like is my idea.
That would make sense. That would make sense. I think you guys could look for something for open source contribution, or for a new paper you guys can do. Albert?
Maybe.
Yeah, Albert, do you have any?
No, I just wanted to say opinions like looks so far a little bit balanced, but number of exams is a little bit too much because
2 exams
and 5 quizzes.
Yeah, the 5 quizzes are just very simple quiz in the beginning of every lecture, of every main lecture, just to see that you guys are still in progress. So that you guys didn't really are not just waiting for the final day of the course to start looking at your lectures. And basically, it's just going to be very easy questions. We're going to see an example of the quiz. It's going to be very easy questions. You just select the right answer, and that's it. If you just assist the lecture, that's going to be enough for you to get those 15 points.
Okay, because I think a lot of people here share the same thing. We are now like we have really short time to finish our diplomas, and we are kind of working all full time to finish our diploma. So
I get it. So if you guys are working already on something related to computer vision, you're not going to have an extra task. So basically, you're just going to have to show me what you guys are working on, and directly that's going to be counted. For the mini projects, they're going to be pretty simple. So for example, train or do transfer learning for cats and dogs. Another one might be to train a generative model to construct new MNIST images. Another one would be to, for later on, we're gonna create like mask detection, image segmentation. Some of the projects that you might be interested in are, for example, vehicle counting. All of these things, we will be doing them. They're very simple. Actually, the idea is pretty basic and the models already exist. So they're pretty well trained. Okay, let me check. Thank you. Can free listeners take quizzes and exams to check if we've learned something? Of course, you can take any the quizzes, you can take the quizzes, you can take the exam with them, and you can also do the projects if you would like and show me. I will not give you like a grade, but definitely I will give you feedback and hopefully it will be useful for you.
I have a question about exams and quizzes.
Yeah.
Will it be model-based?
For now, I'm thinking Moodle-based. So basically, I remember we did the quizzes last year on Moodle. For the exams, I'm not really sure. For the exams, maybe it will be something on paper, very quick. And
like
I will
you send us PDF and we are trying to solve something.
Or probably I will just ask one of my friends at Innopolis to group you guys in the same room. And yeah.
Thanks.
Yeah, we will do something that really makes you guys comfortable, but at the same time, evaluates whether you have learned something useful from this course. The outline of the course. So the outline is very important. This is what I imagine for the course. The first week, we're going to be speaking about classification. So 2D CNNs, 3D CNNs, and interpretability. So we're going to speak about stuff like GradCam, stuff such as LIME and such interpretation methods. We're going to give a little bit of revision on neural networks, 2D CNNs and 3D CNNs. I would assume that you guys know them, but if you don't, it will be a good introduction. After that, we will speak about object detection and mask detection, for example. We will be speaking about the different architectures, RCNNs and stuff like that, and then the different versions of YOLO. I would definitely go for YOLO 1, 2, 3 and speak about YOLO 4 and YOLO 5. But as you know, there are also PP YOLO, maybe we'll touch on that. But basically, if you understand YOLO version 3, the rest of the YOLOs will be very easy to understand, right?
Yeah, so Stefan.
Yeah.
About the YOLO, I think we are not like have to go to YOLO 5 because YOLO 5 is like I may say it's shitposting. And it's like not about like some advance or some progression. Actually, like YOLO 4 is like like forward development of YOLO 3. And actually, I think in YOLO 4 we can just go for improvements what we added.
Yeah, we will see. We will see about this. These things will come in the next few weeks. We will see how which topics should we cover the most and which topics should we just skip quickly. Okay.
Okay.
The third week, we will just speak about general stuff such as GANs. We'll speak about tracking. So this is for object detection. Basically, if you're gonna do something like counting the vehicles and stuff like that, you're gonna require a little bit of tracking. And then we're gonna speak about some facial recognition software and stuff like that. So anything that you guys can use to build your final project or to do something in your future work. The final week, we're going to be speaking about deployment. So in this week, we're going to speak about Docker containers, how to create Docker containers, how to use Kubeflow to train and evaluate your model, how to use pipelines. Another kind of topic would be, so basically evaluation, Docker, Kubeflow, maybe APIs, deployment on, what are they called? Deployment on cell phones and stuff like this. So the steps that you will need to take to do these kinds of things. And trust me, once you finish these 3 weeks, the final week would be the thing that you'll spend most of the work on if you're going to be in the industry. Basically, building an object detection model would take you like 3 days. Deploying that object detection model could take you like 5 or 6 weeks. Transformers in computer vision. I'm actually thinking about adding transformers in computer vision for video understanding. That would be quite useful, but not sure yet. Yes. How, yes, the grading threshold, I will show you guys later the grading threshold. It's pretty flexible, but it's, again, we will see. Yep. So first, I would like to, since I think we've done the let's get to know each other, I made a small Padlet just for you guys to tell me who are you, just a small introduction. My name is, and these are my expectations. If you have any more expectations from the course or something that you would like to discuss, please feel free to say them right now, because right after this discussion, we will start with the first lecture. So if you have any ideas you would like to share, maybe you have a different background than most other people and you would like to get me informed about it.
Let's start the lecture.
Yeah, that's a good one. Let's get on. Before starting the lecture, I'm going to share with you a small link for a quiz. So this quiz is not going to be graded. It's just for you guys to check your knowledge, right? So to make sure that you guys understand the basic concepts of this course. There you go. I sent it on the chat, so you guys can check it. And I will share my screen again to show you guys the quiz. So this quiz is ungraded, and it's just for your personal evaluation to understand what you know, what you don't know, and what you should revise before starting the course. So let's start. You can answer with me as we are going. So as you can see, the question is pretty simple. Computer vision models operate on tabular data, textual data, or images and videos. It's a basic question, just to get you guys to say something. Yeah.
So we're interacting with that quiz. Not everyone.
Yeah, you can do them together with us right now, or do them on your own.
Oh, okay. So,
Yeah.
Yeah, can I say or
Yeah, go
not
ahead. Go
necessarily?
ahead. Yeah, this one is
Yeah, I mean-
easy. So this one just
Yeah, it's like images and videos, obviously.
that's a good one. Yeah. That's okay. It makes a cool sound when you hit the right answer. I think you already passed this question.
It's good to write the question before.
Yeah. So
Actually,
what
we
was,
have 7 questions. 7 questions, yes.
yeah, there should be, I think, 7 questions or 5. I'm not really sure.
7.
So, yeah, I passed all of them. It's 7 questions.
Ah, nice, good. So can somebody tell me what was the first architecture of neural networks that was invented or that was used?
NLP.
Multi-layer.
So multi-layer perceptron. So first there was the perceptron, which then was stacked together in a full layer, and then the layers were combined to make your multi-layer perceptron, something like that. And CNNs, they're made for images and well, they're made for images, and you can also use them for audio and stuff like that. But for our focus, we'll be using them for images. And recurrent neural networks, you'll be using them for all sequential data, especially for text data, right?
And
sorry.
video data also.
Multi-layer perceptron. Yay. Okay, so just another very simple question. What is the algorithm that is used to train and update the weights of a neural network? Everybody should know this.
First one.
Yeah,
Why you have a question 3 of 5, but in total there are 7 questions?
That's a good question. So probably I started with 5 and then I added the last 2 because I thought that would be a bit more interesting. So again, hyperparameter tuning. So this is not an algorithm that's used to train the model. So this is just changing the parameter of the parameters or the hyperparameters of the neural network to give it better, to get better results from it. And the learning rate is one of the hyperparameters of the learning rate of the neural network. Here, I would like to ask a small question. What's the difference between a hyperparameter and a parameter of the neural network?
The hyperparameter we are giving for model to train, and the parameters are trained in model itself.
Perfect. So this is basically the best summary that you can get. A hyperparameter is a value that you set in the beginning of the training and it's stable over there. And the parameters of the model are the things that are going to be learned. So basically the weights of the neural networks that are going to be trained and learned. These are the parameters of the model. The one that we will be using is gradient descent, right? Nice. Are convolutional neural networks hierarchical models? True or false?
Yes.
Nice. So basically, you can see them from the picture here. The first layers of the neural network usually just understand small edges, the shape of, for example, this side, the shape of this side. Then you start by combining them into an eye, nose, and stuff like that. And then you get into the final layers where you will see concepts such as the face and more abstract ideas, right? Also, maybe you could check this one. So for example, yeah, there you go. So these are the activation maps of the different layers of a convolution. And you can see, so it's starting to look first at the small patterns, and then it starts to combine them. These small patterns, combine them and makes the decisions, right?
Look statistic.
I didn't get the question.
No, it's I say this looks interesting. It's very
it's
like
pretty, it's pretty
nice looking.
And that's the link.
Yeah, it's pretty interesting. You will find it also in here. So yeah, in the explanation, usually you'll find some useful information or useful links. Nice. Overfitting is
Both.
fixed using?
Both.
Exactly. So adding more data to the model will help it reduce its overfitting, and reducing the complexity of the model will reduce its capabilities to learn the data. So overfitting means that your model is learning the data and not learning from the data, and reducing its capabilities either with the regularization or reducing the model's complexity will help it generalize better. Overfitting is detected when?
High train, low test.
That's good. This is a bad word.
Dynamic.
Dynamic, yes.
It's not a bad word.
You see, the quiz area didn't let me use this word. So basically, it's dynamic and static computational graphs. Can somebody tell me what's the difference between static and dynamic computational graphs and why PyTorch is better?
Well,
yeah, go ahead. Yeah.
PyTorch uses dynamic. It means that you can, in the Python, using Python API, in the runtime, declare how the functions, the activations, and the parameters are combined. So you can just easily insert a layer. And in the beginning, it was a problem. There was a trade-off between the dynamic computational graph and slow computational graph, and the static, that TensorFlow and Caffe and the previous thing, whatever, and the older one used. So the static. So in Python, you define the structure, and then it was kind of compiled into a static graph, so it was faster. From what I heard, I haven't compared, but now PyTorch is really great, and you still have a dynamic structure. They are on par with TensorFlow on speed, and TensorFlow 2 also tries to shift somehow to dynamic structure to have easier to debug and stuff like this.
Exactly. So basically, PyTorch was very famous at the beginning because it gave us this ability to do the dynamic computational graphs. The very important thing in dynamic computational graphs, it will give you stuff like easy debugging. So if you guys have ever worked with TensorFlow 1, you would spend like days just trying to understand where the problem is. And the error will be in line, for example, 2000, but the real problem is in line 100. So this is the problem with static computational graphs. It's very difficult to debug these things. And it's very difficult to implement new ideas using a static computational graph because you want more flexibility. And flexibility comes with dynamic computational graphs and also easy to debug. So usually PyTorch, it gives you more flexibility, gives you more access, and gives you more control in general.
It's like Python REPL versus C++ without debugger.
Yep. So just a final tip, guys. Please, if you are missing any of the concepts that we have just spoke about, please try to revise them. It will be very easy for you to to follow the course, right? To follow along. Let's start the lecture.
We will have other quizzes in the same way. I like it.
No, but this one is not graded, but it's going to be the same kind of vibes. Yeah, so it's going to be the same ease, I would say. It's very easy. Something that if you just attend the lecture and do just basic following while you're seeing the lecture, you're going to be able to ace these quizzes very easily.
Okay.
хорошо. So image classification with CNNs. The goal of this lecture is just to give you an introduction to neural networks. So, and then we speak about convolutional neural networks, and then some general CNN tips, right? The goal of the lecture in reality is to give you some sort of a timeline of how things are progressing. And in the end, I'm going to ask you a small question, which is based on this timeline and based on the processing that you are progress that you are seeing from logistic regression to neural networks to convolutional neural networks, can you help me or can you give me an idea how to build an easy object detector? Okay, so keep in mind the final goal or the final question of the lecture is how can you follow the same flow of ideas that we will see to build a simple object detector. Okay?
Okay.
хорошо, let's get on it. So first, the first part of this lecture, so it's going to be kind of a three-part lecture. We will be speaking about neural networks. We will speak about stuff such as classification, what's regression. We will see what is logistic regression, and then we will jump into neural networks, multi-layer perceptrons, and stuff like that. To answer the question from the quiz, fully connected neural networks were the first architecture used, and they're commonly known as multi-layer perceptrons, right? And they do provide a very big increase over traditional machine learning. Although this increase, I usually just see it for computer vision and natural language processing. So if you're still using some traditional or some tabular data, I would highly recommend skipping neural networks and going to some more, some new machine learning models, new traditional machine learning models, such as XJBoost and his friends, right? So first, I hope that you guys already understand the differences between regression and classification. So can somebody give me this difference in a small sentence? Yeah, go ahead.
For classification, you have a fixed number of classes, and for regression, you predict not the exact class, but like a number.
Nice.
Between,
Continuous.
Yeah,
exactly.
continuous number.
Exactly.
Discrete versus continuous.
Nice, exactly. This is a great comparison. The thing I would like to say, it only depends on the output of your model. So it doesn't depend on whether your input is discrete or continuous. It only depends on your output. So basically, classification can be stuff like this is a car, this is not a car, detecting the animal, or for example, MNIST. These are types of classification. Another type is regression. So for example, you predict the age of a person, their salary, or for example, the average salary for some sort of a developer, the temperature inside the room, and all of these things, which are float numbers. So basically something that can be, that can have a real value, right? Okay, let's start. So the first model that we will see is commonly known as linear regression, right? So linear regression, just a small question. Does anybody know where did the word regression come from? So where did the word regression come from actually?
I'm not sure, but it's because you regress the original function to a simpler function.
Perfect. This is exactly the answer. For example, for classification, it's very simple to understand why the term classification is used, because you're trying to predict classes. For regression, it comes back to the first study that used regression. So basically, they used the height of the father and tried to predict the height of the son. And once they did the linear regression, they found that the children of very tall people usually are shorter, and the children of very short people are usually taller than their parents. And they are both regressing back to the mean of average height. So this is where the term regression comes from. It comes from the first study that used this technique. And linear regression, what it tries to do, it tries to build a linear mapping between a real value to another real value. So in this case, for example, you take the height of a person and you take the weight of a person and you try to predict their height. So this is a linear regression. Can you guys give me another example of very simple models of traditional machine learning models?
Trees.
Decision
SVM,
trees?
maybe.
Nice.
Naive
SVM.
Bayes.
Support vector machines.
SVM.
What else?
Bias.
Then you said naive Bayes.
Naive Bayes. Yeah, nice. So you guys already have good.
HMM. Human
HMM.
model.
Yeah, that's not a very simple model. I really
Yeah.
hate it.
DB scan.
Yeah, DB scan,
But
that's
it's
a good
about,
one. So this is unsupervised.
Unsupervised,
Nice.
yes.
Can you guys give me something that is unsupervised also?
Hierarchical clustering.
Nice. Something else?
Mean
Something
tree.
a bit more
Density-based
famous.
clustering, DB scan.
K-means clustering.
Centroid-based clustering, yeah.
Nice, nice. After linear regression, can somebody tell me why we cannot use linear regression for classification tasks?
Because it gives us not the class, but dynamic.
Actually, I once read a paper that you can actually use it.
Yeah, you can actually use it. Why not? Yeah.
Yeah, it will train and just run the thing. And it had like a significance, but usually classification is better than regression. But I don't remember why they used it, but it was, you can actually use it.
Yeah, you
somehow.
can do it. Exactly. So there's no problem. Technically, if you take, for example, the x-axis as a feature, as a linear feature or as a real feature, and you take the y-axis as also a real feature, so between 0 and 1, so these are real values, you can build a line like this. And using this line, you will do your classification. So for example, when the line or the y value is bigger than 0.5, you will consider it as class 1. And when it's lower, you will consider it class 0. There's no real difference in them, between them. And even if you build logistic regression, you will get the same results as linear regression. So technically, from a technical perspective. So here you have X, which is trying to predict the probability of X being a positive class, right? So if the probability is bigger than 0.5, then we classify it as 1. And if it's not, we classify it as 0. Why we added logistic regression? It's just for simplicity or for more work after that. Because when you have a value that gives you a probability of 29, it's very difficult to interpret it, or it's very difficult to use it in further analysis. So that's why in some cases, or in this case, we are more interested in getting a probability. We're not just interested in getting a class, but we're also interested in getting a probability. And that's why they added this sigmoid function, right?
Because I think it's more related to the loss, cross-entropy loss. And due to this, we need some kind of probabilistic representation of output.
That's a great remark. So basically, can somebody tell me how do we train linear regression model? Assume that we're not going to use the correct formula, right? So we're basically going to train it using gradient descent.
We try to minimize error.
Yeah, which error are we trying to minimize?
Squared or
Mean
absolute,
square.
something like this.
Which error are we trying to minimize?
MSE.
MSE, mean squared error, right? And here, which error are we trying to minimize?
Entropy loss?
Cross entropy, right? Are you guys familiar with cross entropy and mean squared error?
Yes.
Yes.
Nice, good. So basically, after we got our logistic regression, which what it does, so basically it takes it takes a value in a R in the real space, and it maps it into a probability. Before that, we had logistic regression, which takes a value or which takes a set of values from a space where it's in, for example, R4, and it maps it to another real space, okay? So we have this notion of mapping from one space to another, right? Perceptron is basically just another fancy term for saying, what's it called? For saying logistic regression. So basically, it's kind of the same thingy. We have the input multiplied by numbers, and then we make the sum, and we put it through an activation function. So this is exactly what logistic regression kind of does, right? So basically, the perceptron, or the neuron of a neural network, is just as simple as a logistic regression model, right?
Looks so, yes.
Nice. Can somebody try to explain to me, well, how can we go from a perceptron to a full layer?
With nonlinearity?
No, I mean, I'm not speaking between different layers.
Just stack several perceptrons.
Exactly. So basically, we will stack several perceptrons. So here we have one perceptron. We'll add another perceptron in here. It will have its own weights, and it will be multiplying with the input, and it gives you a different activation value, or it will give you a different value, right? So inside the perceptron, I think you should understand things. What is an input value? So this is your image, for example, or this is your tabular data. The weights and the biases are the parameters of your model. The sum, so this is the first operation that will be used. So basically, we take a value, multiply it, and then we just sum them. And then the activation function. In here, I would like to ask you a small question. What are the different activation functions that you already know? Go ahead.
Easiest one is sigmoid function.
Of course.
Actually.
This one would be the maximum of 0 and x.
Okay.
Yeah. Another one.
There's Relo tan H.
Nice.
And there is a lot of variations for Relo, like leaky Relo and like.
Exactly. So ReLU was really was much more, well, it was better than the others. So basically, they just kept on improving on it further, right? So can somebody tell me what's the difference between sigmoid and tan H?
The scale.
How it maps and how it iterates.
0 to 1 and -1 to 1.
Perfect.
Centered value at 0.
Exactly. Yeah, that's the main difference between these two.
And computational cost.
Which one is more expensive?
Tan.
That, yes, nice. And which one is the fastest for training? So if you would like something to train longer but faster. ReLU, right? ReLU is the fastest. So its derivative is very simple. So its computation is going to be very easy for gradient descent. After we had our multi-layer perceptron, right? After we had our perceptron, people started saying, why not combining all of these things together? So basically taking a perceptron, combining a few of them into one layer, the output of this layer can be considered as future input for the next layers. So basically we have input, we get it through a set of perceptrons. Each one of these perceptrons will give you a value. These new values are considered as the input of the next layer, and so on and so forth until we arrive to the last one. A simple question here would be, why do we put activation functions? So why do we need, it's important to have it, why do we need an activation function after each layer? And what happens if we don't put the activation function?
Otherwise, there will be too much like inputs for each new layer. And
it will be the same thing. It will be the same thing. So activation function, I mean, just the what is it called?
I know, but like we mean some neuron more active, more responsible for each concrete feature.
Okay. Give me another one.
Linear operations is a linear operation.
Exactly. This is the most important part. Combining linear operations will never give you a non-linear operation. So it's going to be the same thing. If you have one layer neural network, with no activations, it's going to be the same as having a 10,000 layer neural network with no activations. It's never going to learn something deeper, right?
I think it's maybe like explained from a mathematical point of view. For example, like we may, in theoretical point of view, we have a function, ideal function, which solve our problem perfectly, like with 100% accuracy.
Yes.
And our neural network is not more than just like a thing which tries to like be this function, to become this function by training.
Yes. And why does using what are they called? Activation functions allow you to how do you call it? Imitate the real function closer.
By nonlinearity.
Exactly. Exactly. So here we are speaking about a concept of linear models and non-linear models. Can somebody explain to me what is the difference between linear models and non-linear models? And give me examples of each.
Okay, like the non-linear models, like starting from like power of 2 and power of 3, for example, like parabola and its non-linear function, and actually like we have a straight line is a linear function, and like the main purposes like come from the derivatives, and actually it's like the like simplest way to understand is this linear function or not.
Can somebody give me a different point of view? So this is correct, but I would like a simpler point of view.
It's non-linear means that mapping from one space to warped another space. When linear cannot warp the space.
Nice.
It's just somehow affine transform or something like this.
Got you, got you. So according to your definition, which one is better?
That could warp because it gives us much bigger
possibilities, right?
Possibilities, yes.
Nice.
Is it like when you have just a hyperplane or hyperplane deformed that has the shapes and not just plane?
Now, I would like to, I like to think about a linear model and a nonlinear model based on the decision boundary that it makes between the classes. So if we take an example of, let's, for example, go here and say logistic regression and just look at the decision boundary that it builds. Let me ask you a question. This is a very good question. Where is the decision boundary of logistic regression? So for example, in this one.
It depends on your threshold.
Okay, my threshold is 0.5. Where is the decision boundary?
At the point that is supposed to be extremum, where you change the rate of growth.
So in here, can you guys see my my mouse?
Yes.
Yes.
So it's just perpendicular to the x-axis.
So basically, you are saying that this is the decision boundary.
No, perpendicular.
Ah, perpendicular. Yeah, sorry, my English is pretty awful. Yeah. So you're saying that this is the decision boundary.
Yeah.
Nice. So this is the threshold, and this is the decision boundary of logistic regression, because the decision boundary is made on the x-axis, is made on the input. So this input is all on the x-axis. We can forget about the y-axis and see that the decision boundary between this class and this class is a linear decision boundary. This is why logistic regression gives you a linear model. Other models, such as, can somebody give me an example of a non-linear model?
Two-layered perceptron.
Nice.
Decision tree, yes.
So decision tree.
Vector machine with a non-linear kernel.
Exactly. That's a great example. Let's see.
Maybe boundary.
I'm trying to look at the decision boundaries of each one of these, but sadly I can't see them.
You could type it. I mean, boundary. Add it to your search.
Yeah. That's a good one. Let's see. Nice. So there it is. Is this a linear decision boundary or not?
Not.
Pachimu.
Because it's hierarchically linear. It splits the space, not because we're speaking about 2D space, it's not splits, it's to two subspaces. It split it to many subspaces.
Perfect. So if we
actually, it's like a linear model, but on each level of tree.
exactly. So basically, we have combinations of linear models. This is what decision trees are. But every single line, just if we consider only this part, this is a linear model. But if we combine the whole decision tree and plot its decision or its boundary, then we will not have a linear boundary, right? So let's get another one. So SVM with kernel. This one. So this is a polynomial kernel, right? So you can see the decision boundary is definitely non-linear here. So this is a linear, this is a line. This is not a line. So this is just the small difference between linear models and non-linear models. Linear models are good for generalization because they're simpler. If your data is very noisy, then you should go for something linear models. And if your data is clean and you have a lot of it, then you should probably go for non-linear models. I'll check the, nice. Okay, let me put it like this, put it back up. Small question. Bigger, wider neural networks always give better testing accuracy than small neural networks. True or false?
Wider or
bigger and
Not
wider.
necessarily,
But they have 2 bits.
because if it fits the data, it will give better testing. Because if you have one perceptron and input a very complex data, it will not learn it, so it will underfit, while the bigger one will fit. But if the smaller one fits and the bigger one overfits, the smaller one will give better testing.
Okay.
So it depends on the task at hand.
Yes, so what we're saying.
Nice.
Yes, it's a classical bias variance trade-off.
Exactly. So this is the term that I wanted to see. So the trade-off that you're going to have to make between overfitting and underfitting. So always choose a smaller neural network. Always start with a very small neural network and add more layers. See how it does and add more layers. Don't start with a very big model and then regress back, okay? Always start simple and then go up.
Actually, recent state of art in like in CV is like EfficientNet and X4D. Actually, like just use this idea, like starting from something simple and then like fit to your problem, make it much larger and bigger, like
Sure.
in this case.
Yeah, that's a good example. Yep. And this is not just for computer vision. This is in general in anything you'll be doing in machine learning. Always start with the basic models. If you're going to write your research paper, usually basic models are very good to use as baselines to show that your idea improves on this basic model, right? So far, what we have seen is the following. So we spoke about linear regression. We saw how can we convert linear regression into logistic regression by adding what? An activation function. We saw how the logistic regression is barely perceptron is just a logistic regression. We saw how multi-layer perceptrons are just a stacked layer of perceptrons, which maps the input into another dimension or into another space that's a bit more cleaned than the first one. And then each layer will be cleaning your data further and further until you arrive to something that is useful for classification, right? Now we will be speaking about convolutional neural networks. And here we will be making the first step of reasoning towards building bigger and more complicated models, okay? So in convolutional neural networks or convolutional 2D neural networks, what we will be doing is speaking about stuff such as padding, stride, kernel size, I assume that you guys know all of these things, so I will go through them very quickly. We will speak about the dimensions, the output of each layer, and then we will speak about also max pooling, right? But the key idea that I would like you to get out of this lecture is convolutional neural networks are just feed-forward neural networks that slide, okay? So there's no big difference between CNNs and feed-forward neural networks besides the sliding part. So the convolution operation, if you guys you had, of course, I'm sure you had a good statistic course with Professor Suchi, you know that the convolution operation is just sliding a filter through your sequence data. And this is what convolutional neural networks do. So basically we take a layer, or we take a layer of multi-layer perceptron and we slide it through the data. This is the key idea that I would like you guys to understand, right? Before we go forward, it would be nice to just visualize how CNNs work. So basically, here we go. Maybe we make it bigger a little bit. This is a very cool visualization that I really like. So it starts with an A. Sorry. And then it slides this filter through the image. And while it is sliding, it is generating the activation map. Can somebody tell me what is happening, or what is the operation that is happening between this filter and the images or the pixels of the image?
It is summing. Sum.
A sum of what?
Sum of pixels.
A sum of multiplication between the values of the filter and the values or the pixels of the image, right?
Yes.
Element-wise multiplication and summing.
Exactly. So, element-wise multiplication and then summing. Does this kind of remind you of perceptron? So what does a perceptron do?
The same.
Exactly. So it takes the input, multiplies it with a value, and then sums everything up. Same thing here for convolutional neural networks. Our shape of the filter, or the shape of the perceptron, is a bit different. So here now we have like a matrix of values. Previously, it was just values laid around. But really, the shape of these values doesn't matter that much. It's how we are using them that makes the big difference, right? So here, what we do mostly is multiplication between the elements of the image with the elements of this filter or this moving perceptron. And later on, we just sum them and send them through an activation function and put it in the corresponding position of the output, right? Nice. So now you will see that we are using a different set of values or a different filter and making a different activation map, right? So this is how we combine, or this is how we make one layer of convolutional neural networks. We take a filter, send it through the data. There you go. We take a filter, send it through the image. It gives you an activation map. Take another filter and send it through the data. It gives you a second activation map. Take a third filter, send it through the image. It gives you a third activation map. These activation maps are later on just smushed together and sent forward to the next steps. There you go. Now we are seeing how we are learning the new patterns, right? And this is what we said before about the hierarchical model of CNN being a hierarchical model. So it's trying to extract different features. Low-level features are extracted in the beginning, and then higher-level features are being extracted in the end. Nice. So basically, this is the moving dense layer or the moving perceptron that we spoke about. Let's imagine that this is our input image, and this is our what? Our moving kernel. So this is the kernel that's going to be moving throughout the image. We perform the multiplication. Sorry. So this is just multiplying with zeros. So this is 0. Multiplying also with zeros, it's 0. So we have 1 of 75, 2 times 80, and 1 times 80. Yep, if I'm not mistaken, I think there's a mistake here. This should be 160. And then we just perform the multiplication and put it in this value, right? So this is basically what CNNs on their core do. Let's stop here and start another discussion of why is this idea better? What does this idea give you?
Locality or data.
Yes, spatial locality, yes.
Nice. Give me more. Throw. The differences between
So
CNNs.
basically, there's two things. First, the use of kernels, the idea of kernel that it takes shared weights for everything. Second thing is the locality. So it can keep the relation between the neighboring pixels.
Good. Can somebody else give me, basically it's the same idea, but reformulated in a different way. Go ahead.
Computational efficiency.
Nice. So now, if we're going to use a fully connected neural network, for example, how many weights will we have? So here in this case, we have 6 weights. In the other case, if we use a fully connected neural network, every one of these input will have its own weight, right? So how many of these? 5 times 5, we would have 25 versus 9. You see the difference in the number of weights or the parameters that you need to train. And again, less parameters, simpler model, better performance, or less overfitting, right? So we go back to the quiz, what we said about the quiz. A simpler model, less parameters, always gives better results. So first thing is we have less parameters. So basically it should give better results. The second thing is, if, for example, we had a cat in this area of the image, the only weights that are going to be training to learn what a cat is are the weights that are associated with these pixels. So for a fully connected neural network. But if we're using convolutional neural network, it's the same weight that is learning in this area. Sorry, go back. The same weights that are in this area, learning in this area will be used in the area of the face of the cat to learn how to identify a cat. So basically, if your object is somewhere inside the image, your weights are definitely going to be using it to train. Unlike for fully connected neural network, most of the weights will be useless. Most of the weights inside the input layer will not be interacting with the objects inside the image, and hence will be only giving you noise later on. Can somebody else explain a different idea? So this is the first idea of shared weights. Another idea. Why CNNs are better than fully connected neural networks. Go ahead, guys, come on. If I'm not mistaken, most of you guys took this exact question with me exactly. So you should already know this. I know that you guys know this. So you're not going to be like, our professor did not teach this before. Go ahead.
Give a hint. Because there are many.
Equivariance, amazing. So Mustafa said equivariance. Can you explain it, Mustafa? Continue, guys. Come on. Just give me your opinions. Throw it. There's no wrong or right opinion. Just tell me why CNNs are better. So we said the weights are shared. The weights will be learning from the object wherever it is inside the image. Maybe something else. let's imagine a different scenario, okay? What if this idea of, for example, the shape of the filter was not a rectangle like this, but for example, was just a line, okay? Was a line walking around. How would that differ? Can somebody tell me what the relationship between the pixels like this, instead of seeing the relationship of the pixels as a flat array?
Maybe you can see a corner or something like this.
For example, if, for example, we take my nose in here. So there
the
are
shapes.
exactly
Shapes.
exactly.
And we use it
Yeah, exactly.
to
Perfect.
move from one step to another. We recognize a shape of a nose and later recognize entire nose, and later we are working with same ways.
Exactly. Perfect. This is
Face.
it. Yeah. Yeah.
And
Yes.
it's working identically with our brain.
Yeah, exactly. So basically, when you represent an image as a flat array, you lose the information of the connectivity of the pixels. So in the nose, this pixel is close to this pixel, is close to this pixel, but if you flatten it, you're going to lose this relationship. When you keep it as an image and walk through each patch together, you're going to keep or maintain the relationship between the pixels which are close together. And this helps you build better models for understanding shapes, right? This is a great idea. Yeah, thank you. So now we will speak about just two small concepts, which are padding and stride. Previously, we were walking step at a time, right? We were walking one step at a time. There you go. So it's walking one step at a time. Can somebody tell me what stride is, right?
It's how many steps you are doing at a time.
Exactly. So instead of, for example, going from this pixel as the first and then going to the next pixel and the next, we jump 2 pixels. We just ignore this box, right? So this way we reduce the amount of computations we have. And what else does it give you? What does stride give you? So less computations.
Output.
Yeah, smaller output. So basically less computations right now and less computations for the next layer, right? And it helps
for now.
Yeah, and it helps you also remove redundancy, right? So for example, if you take this area of my face and you just move with one pixel, you're not going to find a lot of differences, right? So basically, when you use stride, you're going to be removing some of the noise or the repetition that you're going to be finding, right? So this is why using stride is very important, especially in the beginning layer, in the first layers.
And actually, it's like the same thing for temporal like data, not only for images but also for videos. Because like if you have like neighbor frames, it's no big difference between them. There's no information for you.
Here is any rules how to select stride. I mean, maybe when I have a lot of small features, it's better to select small stride or something similar.
This is a great question, and the answer is never select your own stride, right? Because selecting your own stride means that you're going to be training your own model from scratch. You're never going to get a good result training your own model from scratch. So usually use any
except if you are not a Google.
Yeah, except if you're like at Google or at Facebook, and you will be giving us these pre-trained models, right? So any other situation, you're gonna have to use the model that Facebook and Google gives us, and we just use that and build on top of it, right?
And actually, like the different strides actually is a good way for experimenting, and actually like is good way of combining different strides. So actually, strides is one of the most efficient like ways of combining something new from life.
Exactly, true. And the bad thing about changing the stride is because it will really dramatically change the size of the output. And hence, if you're going to be using stuff like Keras and stuff like that, not Keras, I think Keras is clean. If you're going to be using a framework in which you specify the input dimension, then you're kind of, if you change one stride, you're going to have to change the whole architecture. So that's a bad thing about changing the stride. I see that Mustafa sent a message on the chat. saying that equivariance, if the object is in the picture, for example, its features will get picked up, but if the object is not there, the output feature map will not contain this object. I like this definition. I will not go into more details in this one, but if somebody is really interested in this concept of why CNNs are not good, so what, not why CNNs are good, so why CNNs are not good, there's a new field. It was new like last year. It's called capsule neural networks, which aim at not using equivariance, but I forgot the term for it. It's just another type of variance. So basically, if you'd like to understand why CNNs are not good, go read the paper on capsule neural networks. It's made by Geoffrey Hinton, so the guy who created backpropagation. So he's kind of the god of neural networks, and he's saying that the CNNs are not useful and they're not good. So it will be kind of a good area of research for those who would like to continue in research. Check out capsule neural networks, right? Now, the second concept is padding. Can somebody tell me what is padding and why do we use it?
It's just adding some like margin to,
exactly, right? So let me
to corner calculation.
Yeah, exactly. So like this, for example, we assume that this image, this is the image, and then we just add it with zeros. We just pad it with zeros, right?
Yep.
Not only with zeros, like it's like different strategies for padding with like more information, because like so we may be not interested in like reducing the size of like information, the number of information we can analyze. Or maybe we want to be able to analyze not only like but center information, but also like the edge information. In this case, we also need to have padding. Like padding
Yes.
is like golden hammer.
Exactly, got you. Can somebody tell me what are the different values that can be used for padding?
Zeros.
Fixed value
Yeah,
for the
same value.
nearest pixel.
Perfect. Yeah, perfect. You guys named them all. So basically zeros, fixed values, or just repeating the edge.
Yes.
Repeating the edge. Again, we said that if we would like to augment the size of the output, so if we can calculate it here, just let's do it together. We have 3 by 3, it translates to 1 pixel. Another 3 by 3 translates to the second. Another 3 by 3 translates to the third. Can somebody tell me if we use convolutional neural network or convolutional transfer of 3 by 3 on this image, what will be the shape of the output?
It will lose 2 from each side. So it would be 3 by 3.
Exactly.
Where is it here?
So when we take an image of 5 by 5, send it through a kernel of 3 by 3, the output will reduce 2 pixels from each side, and it will be a 3 by 3 image. If we want to maintain the same size of the input is the same size of the output, we can add padding and to fix this problem. Can somebody tell me what's the padding required to maintain the output to be 5 by 5?
1.
Yeah, 1 in each direction, right?
Yes.
Yeah, exactly. So basically 1 from this, 1 from this, 1 from this, 1 from this. And once we apply this 3 by 3 filter, we will remove 1 from this side, 1 from this side, 1 from this side, and go back to a 5 by 5 layer. So as we said, it's used for augmenting the size of the output or for increasing the focus on the borders. So in some cases, the main or most cases, your main focus should be on, or the main object that you would like to classify should be inside the center of the image. But if for some reason your objects are kind of hidden in the background or like in the corner, and you would like to focus more on that kernel, on that corner, then you should add padding to understand better, right? Or to help the neural network focus more on this area. The dimensions of, I think, something is wrong. I thought that I had the dimensions here. Okay. CNN, visualize. No, sorry. there is a problem in the slide, but basically let's just ignore this text and focus only on these guys, right? So can somebody tell me what's the dimensions of the output of a CNN directly? So without padding, without stride, without max pooling. So basically
The
you have
kernel -1.
not always. Let's check, right?
It depends on the filter, right?
Output of CNN dimension. Let's take something simpler. Yeah, let's take this one. So let's assume this is W and this is H, right? And you apply a filter of, let's call it, no, we need something X and Y. So let's say this is X and Y, and the filter size is W and H. What will be the size of the output? It's very
It will
simple.
be X minus H plus 1 and
Okay.
Y minus W1, which is the like it will decrease the kernel -1.
Good, amazing. So basically in this case, what we have is the following. We take, for example, this is X and this is W. As you can see, so here, this 3 reduces the number of pixels you can take, right? So you can take these 3, you can take the next 3, you can take the last 3. So basically 2 of these pixels will be ignored. And this is what reduces the size of the image. This number 2, if you change it from, for example, 3x3 to a 4x4, let's try it. So we put a 4x4 in here, and the only other option is to put another 4x4 in here. So how much did we reduce? We reduced 3 pixels. Hence, the formula for this one is X minus W plus 1, Y minus H plus 1, right? So this is the output of a CNN or a convolutional operation, just one CNN per kernel. Let's add padding into it. So how does padding influences the formula that we just described? So let's write the formula first. So here it is, X minus W, right? Plus 1.
Plus, please.
Where do we add the padding? How does padding influence the output?
We just
W
plus 2.
Yeah, it should be here, right?
Plus
So
2 padding.
If we ignore the fact that the padding is added and just treat the padded image as a new image, we will find the formula changing like this, right?
You also need to put 2.
Why are you adding padding
Should
from
be
one
2.
side? You have to
Okay,
add it
got
from
you.
both sides.
Correct. Sorry, like this.
Yeah.
Nice. So if we have a padding of 1, so we will add 1 from each side. Correct. So this is how the formula changes according to padding. Can somebody tell me how does the formula change when we add stride?
Divide by stride.
And take the lower
But
bound.
not all except the one.
Let's try it. Let's see it here and understand it better, right? Let's see it here. Nice. So if we say that we will have a stride of how much? Of 2. Then the only options we will have is this object, is this box, plus the last box. So our output will be 2 by 2, which is, again, as you guys said, so X, which is 5 plus 0 minus what? Minus 3. 5 minus 3, which is 2, divided by the stride, which is 2 plus 1. Sorry. So this is the formula for the output of a convolutional layer, right?
Yeah, we remember.
Nice. So I don't want you guys to remember it. I want you guys to remember how to generate it. So basically, if during the exam or during some quiz, I will either give you this formula, or if you don't have this formula, then try to regenerate it from your brains, okay? You don't need to remember the formulas. You need to understand the logic and the steps needed to generate the formulas. Nice?
You just need to add the lower bound. So when you divide, you need to add lower bound.
What do you mean?
If, I mean that if your image cannot be treated like exactly, you drop the last part.
Got you. So for example, if we chose for in here, if we choose a stride of 10, then we will only have just one, right?
Definitely.
Exactly. Nice. That's a great remark. So basically, here is the formula, the final formula. So it's the input plus 2p minus k divided by s plus 1. So k is the size of the filter, right? In this case, they assume that w and h are the same, and x and y in our case are the same, so they don't change. I will update the slides to basically put the steps of the formula and how do they evolve. For max pooling, let's start by speaking about what max pooling is, and then we will see what the output of max pooling, what the dimension of the output of max pooling should be. So max pooling simply takes, for example, if we take a max pooling of a filter, it slides a filter through the image and summarizes the information in these pixels into one value. So basically it ignores the rest and takes only one value, right? So if we use the max pooling with 2 by 2, we take this area. What is the biggest number here? 5. We only keep 5. We ignore the rest. There is another type which is called average pooling. So basically we take these 4 values, we take their average and put it in the output or the activation map. Basically, yeah, so here it is. We take the filter, we slide it through the image, and we take the maximum. A small question. Does max pooling or a max pooling layer have parameters? If yes, how many parameters does a max pooling layer have?
No.
It have no parameters.
It has no parameters.
I would say it has the stride and maybe dilation.
No, these are the hyperparameters.
Okay, then it doesn't have.
Exactly. So parameters are those who are being trained. So max pooling is not being trained at all. It's just an operation which takes the image, takes the maximum of like a group of pixels and puts it out. That's it. It just reduces the size of the image. Basically, it reduces the computational cost drastically. And more importantly, it also helps you reduce the noise. So basically, in this area, we had a kernel or we had a filter that looks for the nose, okay? In this area, the nose was found in this pixel. Why should we worry about what's in the others, right? So basically, the highest activation is usually the location of where this kernel has made its detection, right? So that's why max pooling works very well, because it allows you to focus only on the maximum area or only on the place where it had the maximum influence, right? So let's predict the output of max pooling. Can somebody tell me what's the output of a max pooling layer? So we will assume that the size of the image is a rectangle. It's going to be X in both directions. And the size of the max pooling is, let's say the filter. The filter would be W, or yeah, let's call it W. And the stride, we will not speak about it yet. So only X and W.
Is the same formula as we have before?
Nice. And the stride?
Still the same.
Still the same formula. So basically, it's the same kind of operation as what? As convolution, right?
Convolution.
So it's basically taking a filter and mapping it through the image.
It's just another kind of filter.
Exactly. But in this case, the filter is not a set of weights, but it's a function.
Yes, of course.
Nice. So now do you guys understand the difference between max pooling layer and a convolutional layer? They're pretty similar. One doesn't have weights and one has weights. Can somebody tell me how many weights are in a convolutional layer? For example, in this one.
9.
10.
10.
Точно. Yeah.
That's a good
And
question.
multiplied by number of filters.
Exactly.
If
So
we say
first,
that layer.
we have this plus the bias, right? So in here we have 10 weights to learn, or 10 different parameters to learn for this special kernel. And then for as for example the image, usually images are not just what are they called? Are not just one channel, grayscale. They're usually RGB, so 3 channels. Same thing can be said for these kernels. So we basically don't apply just one filter gives you one output. How about applying multiple ones of these and getting a lots of channels in the output? So this is how you create your convolutional layer, by stacking a set of filters of usually the same size. There are some models which use different size filters inside the same layer, but in most cases you're going to have one layer of convolutions stacking a set of same size filters. Each one of these filters will probably be learning something different. So one will be looking for the nose, one will be looking for the eyes, but they're both very useful. Brackets in formula for dimension. Calculation mean integer part. Yes, exactly. So the brackets in this formula. Yes, the lower bracket in the formula can be treated as either the integer part or the rounding to the lower value, right? Nice. So far we've seen linear regression, logistic regression, and again, perceptron, multi-layer perceptron. And then we've seen how did we go from perceptrons and fully connected neural networks to convolutional neural networks simply by sliding our perceptron through the image. So you see this idea of sliding. I would like you to continue with this idea of sliding. Before we go to convolutional neural networks 3D, can somebody tell me where are they? What are these 3D images? And give me some examples of these things.
It's either 3D
Well,
files or
Videos.
Videos, 3D MRI
files.
scans, stuff like this, right? So basically, can somebody also tell me, if we take an image as just a matrix, a 3D volume, how can we process it?
Simultaneously, several images, several frames in time.
Exactly. So basically the same idea of sliding, we use this same idea of, so basically these are the applications of the differences between CNNs and 3D CNNs. And instead of having a small object, which is just sliding in one dimension of the image. So basically previously the sliding was X and Y. Now we will have a cube that is sliding in the X, Y, and the Z coordinate. The Z coordinate can be the time, can be, for example, if you're using MRI scans, then it's basically the X, Y, and Z coordinates of the MRI scan, or the different axials. So basically here, your filter or the filter size has, for example, in this case, 3 by 3 by 3, right? And then it gives you one output in the activation map. Same thing, a layer stacked after a layer, after a layer, after a layer. And then what you get, then your final value will be just flattened and sent through a fully connected neural network for classification, right? So now that we've done this cycle, can somebody please tell me, how can we build, or following the same ideas, how can we build a simple object detector using this sliding idea?
Let's slide with the window.
Nice, yeah. So basically what we do, we take a classifier and we just slide it. We take a 2D CNN and slide it through the image. So the image now is not the input to the classifier, but only a small part of the image will be handed out to the classifier. And wherever the classifier says there is an object in here, we take the coordinates of the window that we've chosen. Keep this idea of sliding window object detector, because this idea will be very useful for us for the next week to understand the newer models and to understand or how to evaluate these newer models, right? So if you guys want to do a little bit more reading, these are the resources I use to make these the slides. I will update the slides and put them on Moodle. And if you guys have any more questions, if you guys would like to have a small discussion, please feel free to do so right now.
And which resource you recommend first order?
That's a good question. I would not recommend any of these sources, to be honest. If you would like to learn more, I would recommend you the Coursera course on advanced computer vision. So this is a very good course. It's done in TensorFlow, so it's not very, I wouldn't recommend TensorFlow for lots of applications, but still, the concepts there and the algorithms which are explained in that course are very well explained and very easily explained. It's much better than text, for example, for my case. But if you guys would like to find a good text, so this deep learning book definitely is a very good text resource. If you're not into text and into videos, then just go to the Coursera course on advanced computer vision and in TensorFlow.
Matt, could we guide the lectures? I mean, after some number of lectures to the topics we're interested in.
Of course, you can do it right now. Actually, if you have any certain topic that you'd like to cover, please tell me. We will cover it together. Yes.
Yeah, I have written it in the chat. Networks
Nice.
optimization and compression.
In the chat of
our chat.
Okay, in the Telegram.
In Zoom.
Okay.
Networks optimization and compression.
In the beginning.
Techniques for distillation.
Yes, this will actually we will cover these things in the final week.
Oh, it's cool.
Yeah.
Maybe we will make some kind of pool, because some topics are interesting for a couple of persons and some topics are interesting for most of the person.
Yeah, we can do that. There are
maybe voting.
Voting for topics.
Exactly. So we can put a small poll on the Telegram channel, and basically you guys just vote for any topics that you would like to see covered, right?
But how can it
There's
work?
multiple choice.
We have different groups, so we will have these pre-votes. So there is the one group for robotics, for example, who are interested in edge devices and edge inference.
Yes.
The other group. So we don't. If we vote, can we just say we want this, and that, and there are groups. So
there are more days, guys.
I wouldn't really think that this is possible, but I would think that this can be done through different areas of projects. So for example, the guys of robotics can focus on these things. All of us should see concepts such as deployment on edge devices. This is very important, whether you are in robotics or you're just going to be industrial developer. This is a very important concept to learn. I think the basics of the theory should be the same for mostly everybody, but how much you focus on each one depends on your project, depends on the project that you will choose.
Can I please ask to maybe cover later in the course when we will talk about the edge devices and the portability of neural nets, to cover a bit in deep how to port existing architectures that require some maybe non-trivial layers to mobile devices. Because, for example, as far as we know, PyTorch, especially PyTorch script, doesn't support a lot of operations and a lot of, yes. So how can we overcome this?
And this problem is not just for mobile phones. It's, for example, I ran into the same problem with a few servers. So basically, if you have any server that is older than 2017, you're not going to be able to run any of the new models such as YOLO v4 and all of these new models, because they require some computations on the GPU that don't exist basically on old GPU devices. So we will try to cover many of these. We will speak about model conversion between frameworks. So in some cases, if you just can convert it to O1NX, for example, or TensorRT, you're going to be able to still run a highly complicated or highly different architect or new architecture on a old device or on a simpler device, as you guys are saying. So we will definitely cover a lot of these things. We'll spend a whole week only on the problems that you'll be facing on deploying such different models. So basically the first weeks, we're just going to be using Colab a lot. Colab is already pre-configured and it's optimized for lots of the recent computations. Later on, we will see how you can do this on different servers, on your local machine, on the, for example, on the, what is it called? On the browser, on the cell phone, and on edge devices. Especially on edge devices, there's a lot of importance in these things, right?
Mm-hmm. And I also seen you mentioned Kubeflow. So
yeah.
How can we run this? I mean, if we are not equipped with a cluster?
That's a good question. So from my side, what we're going to do is we're going to run Kubeflow locally. It's not going to be that much different. So what I'm going to try, I'm going to see with the university if we can set up a small cluster just to have the installation of Kubeflow ready for you guys. And you just take your pipeline from the local machines to the university's machines and see that there's no big change in there, right? I might show you also how to use, for example, S3 and how to use, what are they called? ECR and different container repositories. How can you connect them to Kubeflow and these things? These are very important, especially if you're going to an industrial company. Or for example, for those who are already in here from a company and they would like to adopt using Kubeflow for their training, it's very important now to start using pipelines for training. It's going to be a help to train neural networks and object detection models directly on each run locally, you know?
We agreed.
Are you guys familiar with Docker and stuff?
Yes.
Yes.
Oh, that's cool. That's pretty cool. That's pretty cool. Then
we made our own Docker.
What?
We had course where we made analog of Docker.
Ah, that's a bit too advanced. No, take it easy.
Our Docker image is like 30 gigabytes that we use for development. So
that's cool.
That's not cool. That's not.
I would recommend if you guys don't have a Linux device, you're going to suffer through the Kubeflow part. So I have a Mac, and usually if you run any Hello World Kubeflow algorithm, it will take all the RAM. I haven't done it on Windows, and if you are like in masters, you shouldn't have Windows right now. You should either have Mac or Linux. So for Windows developers, you're also going to find some problems later on with Kubeflow. Take it easy. So try to find a Linux installation or maybe like dual boot and stuff like that.
If you're a Windows developer, you have to suffer.
Yeah, you deserve to.
There is a vendor called Linode, Linod. They have some giveaways. Not giveaways. They have a lot of promo codes. They give up to $100, and it may be sufficient to run somewhat powerful machine for a few hours.
Oh, that's nice. We can try these. Yeah. So basically, right now, this is an open discussion. We finished the lecture. Anything that you guys would like to discuss, would like to share? Nice. Thank you, Nikita. I'll actually check this one. Yeah. Anybody else has some concerns, maybe some questions?
Maybe I can add that there is a good course on Stepic platform, which is connected with computer vision. It from Samsung research team, from Russian Samsung research team. And if you know Russian, there a really wonderful cover of the basics, math theory, and some practice of computer vision if someone is not familiar with it.
Yeah, exactly. So Stepic, I think it's like Udemy for Russia. It's pretty interesting. It's very, very interesting, to be honest.
Yeah, there are two courses. One of these courses is connected with computer vision and another is for NLP problems.
Got you.
Deep Learning School?
Could you repeat, please?
Deep Learning School from MIPT, you mean?
Give me a second, I will check.
Imad, may I ask a question?
Yeah, of course, go ahead.
we will go deeper in 3D CNNs or in some kind of video processing.
Yes,
Oh, no?
we will go deeper in these things, but in what is it called? In the lab. So basically, we will have a lab on 3D CNNs where we see, build a 3D CNN and train it.
Okay.
Yeah.
The course is called Neural Networks and Computer Vision, and in Russian нейронные сети, компьютерное зрение, название курса. So you could try, and there is a lot of useful information for the beginners.
Oh, that's pretty cool. I haven't heard Russian in a long time, so it feels nice to hear it again.
So close to my heart.
It's time to learn Russian.
Mhm.
Imad,
Yeah.
we will have a lecture tomorrow in 12 hours, yeah?
Yeah, exactly. So the next lecture will
Perfect.
be in 12 hours. You guys already have the program, right?
Program, you mean the schedule?
Yeah, the
Yeah, we
schedule.
have.
Nice.
12
Good.
hours? It's not morning?
Oh,
Let me see.
thanks God.
So, at 8.
Yeah, early morning in 12
Yeah, I
hours.
should have called, like I should have said no. I do not like to wake up early.
Not
Imad,
only-
it's a problem to you because if like we just like say this time is Moscow time and you like living on the zero for Greenwich, it seems to me was you need to wake up at 5:40. Yes.
No, I need to wake up at 7:40. Yeah, there's just 1 hour difference between us.
Yes. Okay.
Yeah, it's okay. I can do it for you guys.
If you want, and if everyone will agree, we can move to.
I was going to complete.
I think this change would be too. Yeah, I think definitely this change is very needed, but changing the session for tomorrow would be too fast of a decision. So let's agree to change the sessions as of next week, because I think it's every week like this. Every week starts at 8:40. I don't know who made this program. Somebody who's really likes to wake up early.
Some crazy person.
Yeah, crazy
Who-
people,
who
guys.
wake up
really.
at 7.
Yeah, I
Super
mean,
optimistic.
it would be great to split if we have one lecture on Friday and three, like better 2 and 2, I think.
We can. Can you guys? Are you guys feeling that you can study a bit more even right now?
Not on Fridays. We need
Not on
to go
Fridays,
to
huh?
dream.
Yeah, exactly. Like your head is probably just dying currently. So let's consider 1 session on Friday, 3 sessions tomorrow, but we will give more space between the sessions, okay?
Nice. I like it.
Хорошо, хорошо. So thank you guys. If you guys have any recommendations, any remarks, did you guys like the format of the quizzes? Did you guys like the format of the lecture? Do you guys want more textual content in the lecture, or do you guys want more graphs in the lecture? Please feel free to share all of these opinions. Yeah, Nikita?
I think the only thing that you should not forget to upload the materials to Moodle, including the video.
Yes, so the quiz, the video, and the PDF will be
And the
uploaded.
slides. Yeah.
Yeah, got you.
Thank you very much.
Хорошо. Oh, Marina.
Thank you.
Are you Marina like my old student?
No, it's not me. It was
Ivanova.
just like
Yeah, that's good though. So yeah, so the one who just texted is not my old student, sadly, but Marina Ivanova, I think, was my old student.
There are 3 Marinas.
Yes, I am.
Ah, cool. How are you?
I'm good.
Ah, nice. It's really nice to see you guys again.
You see the names.
So that's it, guys. Thank you guys again. If you have any questions, please feel free to text me. Maxime?
Yeah.
Go ahead. Or Nikita, I
No,
guess.
I mean, thank you.
Ah, thank you. Nikita?
Can I leave with you and the 3 of us to talk
Of
about
course.
the industrial projects and stuff?
Yeah, of course. If you guys, yeah, for those who we finished the
Just
lecture.
do not forget to stop the record.
Ah, okay, yeah, that would be good. Yeah, let's stop the recording.